Lin from NTHU University. He will talk about searching for high-Z galaxies in the cosmology field. So let's welcome him.
Do you guys hear me? Okay, thank you. So, good afternoon, everyone. Thanks for coming. So, my name is Seong Jin from Tsinghua University, and today I'm going to talk about our recent work searching for high-redshift galaxies in the cosmology field. So, this is about the dropout galaxies using the z-20 NearCam filters, and this work was done with our collaborators in Cosmology group and data reduction team, especially Zenkai, Claude, and TC and Wei Hao. So the questions about how galaxies have evolved and how they have formed the stars. This is one of the hardest issues in modern astronomy, because we want to understand the star formation history of the universe. So this is one of the most important and interesting questions. So this is kind of a simplified history of the universe, and which tells us that the star formation activity in the universe peaked around redshift 2 and then decreased afterwards. And if you look at the wider range, including high redshift, we see that there's uncertainties in here. So many different work shows different star formation efficiencies, and recent work, especially recent work, shows much lower star formation efficiency compared to the Bada et al. So now we are looking at the higher redshift. So the questions becomes like this: when the first galaxies were formed. So this is even more interesting because this is about how to understand the first generation of galaxies. So we actually want to know where we can put the data point here. So to answer these questions, we have to observe the distant galaxies in the early universe here. Then how we can do this? Here, JWST. So this is one of the most advanced telescope ever, which is optimized for infrared observations. So it has much improved sensitivity and resolution. So we want to put the data points here, the redshift 20. So it's okay, but actually it's not that easy. This diagram shows the theoretical study predicts that in 90 square arc minute, the discovering even a single galaxy is not that easy, because only one galaxies are expected, or even far below that. But Cosmos field covers 20 times larger than 9 square arc minute. So maybe we can expect 20 times larger already. So Cosmos covers 0.5 square degrees. This is even, compared to the previous early release data, it is 100 times larger. So maybe this is one advantage we could take. But even without any proper data reduction, this could not be possible. But thankfully, we have data reduction team here. So I would like to thank Zenkai, Claude, and TC. Actually, they gave me the data. So this is actual image data, 2.7 micron, and this is how it looks, 2.7 micron, after the proper pipeline reduction. And how we can search for the high redshift galaxies. In this work, we focused on searching for the galaxies which have nanobreak features between these two bands. So in this work, we actually tried to find 1.5 micron dropout, and this is the key part. So you can see the 4 filter bands used for the Cosmos Web survey, and this is example nanobreak galaxy. So what we want is this, the reliable detection in these two bands and non-detection at the shorter wavelength band. And this is what we want. And all these kind of criteria can be summarized using color flow diagram. So our candidate has to be located in this area defined by these three lines. So vertical line, this line, and horizon. But this line, horizontal line, indicates the dropout at 1.5 bands and robust detection in 2.7 micron band. And the color has to be at least larger than 1. This vertical line explains the shape, LCD shape. So the LCD shape shouldn't increase stiffly from 2.7 to 4 micron, but the color has to be smaller than 1. And this line compares the color with these two colors. So flux drop in these two colors on y-axis has to be larger than this color. So these criteria can exclude some low redshift sources around here. So in addition to these criteria, we excluded the sources that have some photometric information in the short wavelength band. So we excluded the sources that matches to the Cosmos 2020 color. And then we also excluded stars based on the flux ratio and magnitude, based on the, as presented in the Weibo in 2024. But still, there's a possibility that the bad candidates can be included in this area. So we carried out visual inspection. This is needed to exclude some bad kind of artifacts. And then we carried out a CD fit. We used the Seagull, and this is an example, but quite challenging because we had only 2 data points. But thanks to this break feature, we were able to obtain the photometric redshift and some physical parameters. So background level in shorter 2 bands used as an upper limit. So this is one result. So this diagram shows comparison of the actual number of brighter galaxies than 220 in magnitude against the theoretical prediction. And this is our result, 1.7. So compared to the previous work in Harikana et al., it's shows a smaller number, but still it is slightly higher than the theoretical prediction, which suggests that this kind of theoretical predictions kind of underestimate the abundance of bright galaxies in the early universe. And this is one of our SED field results. And our candidates appears to have a wider range of photometric redshift, 48 sources between redshift 12 and 23. So we have 48 sources. Compared to the previous work, for example, Harikana et al., 2023, they used all the dropout technique and 22 sources. So, but we have 48 sources. This is kind of the advantage we are using the larger field data. And this is interesting results. The UV continuum slope data defined at the rest frame UV bands. And this is a relation between the UV continuum slope against absolute magnitude. So our candidates have the beta value normally smaller than -2 here. So many of them are smaller than -2.5 and even close to -3, which means that they are really very blue galaxies, which are expected to be star-forming galaxies with minimal dust content. So, and then we finally estimated UV luminosity function in 3 different redshift bins, and then compared it with some other similar redshift range. So this red curve is a shift function describing our data points, and then integrating this shift function gave us the star formation rate density at this higher ratio. So thanks to the power of the JWST and large field of cosmos field survey data, finally we have star formation rate density at the ratio of 20. This is our final goal, and this shows the power of JWST. So if I had more time, I think we can talk about a little about this. Except for this work, you can see, we're going to have another science talk based on the cosmos field data. Later today, I think our students are going to talk about brown dwarf and protocluster candidates, and they are really interesting talk, very nice. So you can enjoy them too. Thank you very much.
Thank you, Seong Jin, for a very nice talk. Any questions from the audience? You can use the microphone in front of your desk. Yeah, go ahead.
Thank you, Seong Jin, for the talk. So if we found galaxies at redshift like 20, does it mean that we have to rewrite the entire galaxy formation theory?
Not entirely. I think this is, we need more data, but some sample observed by JWST says there's a little modification or not, something like that. For example, this kind of things. Previous theoretical study thinks maybe we can see this kind of number of bright galaxies, but observationally, sometimes we obtain a larger number. For example, like this. So we need to maybe some modification, star formation or galaxy evolution theory. Maybe we need some modification.
Any other questions? Yeah.
Thank you for the talk. I'm just curious about the stellar mass of the galaxies based on the reading. Do you calculate massive or?
Actually, we have stellar mass and star formation rate, but they are actually, very, very well aligned in some line. So maybe we can, but we actually focused on this one first because we have only 2 data points. So maybe defining the slope is quite reliable. But actually, star formation rate and stellar mass, maybe we can discuss about later, but not this time. So we just not really focus on these 2 physical quantities. We just focus on the physical quantities in here.
Maybe one last questions.
But they are very bright and massive.
No, if not, then let's thank Seong Jin again.